Hello, welcome to Module 10, when we'll talk about big data. And in this lecture we'll focus on how you can deal with large data sets which may be hard to fit in your computer's memory. And so we'll look through some specific strategies to handle these large data sets, how to optimize your memory usage. And the overriding theme here is that while you might associate, if I want to do data science, I need a really fancy piece of equipment, or I need to have a cloud server or something. Most data science applications you can do with a little bit of care on your own laptop. And so what I'm going to talk about here is strategies so you don't really need these outside computing resources. You can do as many analyses as you can on a regular laptop computer. So big data is often characterized by what's called the 3 V's. So velocity and volume and variety. Velocity is how fast this data is coming at you. It's like a fire hose of data. We're not going to talk about that here. Variety we've talked about quite a bit throughout this course. How you clean and join and wrangle data sets which aren't necessarily ready to do so out of the box. So in this lecture, we're going to focus on volume. In short, what you can do when a data set is too large to easily fit in memory, or computationally, what happens if your code just takes a long time to run. So I'm going to set out a hierarchy of approaches to dealing with large data sets. And so the cardinal rule is start with the simplest one, and then only move on to the next group of solutions as you need to. As always, follow along with the code in the notebook, which is available to you on GitHub. So the first one is test and scaling up. So rather than run your sentiment analysis on all 500 of your climate action plans, just do one small one, get it working. And then you can scale up once you're ready. Something simple, just leave your computer to do this overnight. You don't have to watch it all the time. You could spend a few hours trying to speed up your code so it runs in half an hour. Or you can just say, hey, I've got better things to do in my time. My laptop can sit in the corner while I'm getting some sleep or doing something that's fun. You could find a secondary computer. Perhaps you have an old computer which has a cracked screen that you can just leave in the corner to run over a few days, or borrow one in a lab. Perhaps and this is particularly important for something like web scraping, where you have to leave the computer running for a long time if you want to capture, say, more recent Craigslist posts. Get an old computer, just run it in the background, put it in the corner of your office or apartment, and as long as your internet connection doesn't die, that's going to be happy chugging away while you do something better with your life. The next one I mentioned just briefly, because we're going to discuss this in more detail in the next lecture, is profiling. And that's how to identify bottlenecks in your code and figure out where to speed things up. But in this lecture, we're going to focus on large data sets and how these can fit in your memory through judicious use of data types and of sampling. So what's a data type? Well, a data type is how an object, like an integer or a string, is stored by Python. So if we're using pandas, then that generally uses the underlying NumPy data types, which are described in the NumPy documentation here. So we have bool, byte, unsigned byte, and so on. And each of these data types have a certain memory or space requirement. Normally you don't need to care about this. If you have integers, then often storing them as a float will work just as well. But we've seen several instances where we do need to convert the data type. For example, if we have numbers stored as strings, we need to convert them to integers or floats to do some mathematical operations on them. We've also seen with census identifiers like tract IDs, they can be stored as numbers, as floats or integers, but then you lose the leading 0 in an ID like 06075. So for example, if we try and multiply x here by y, notice these are strings. So we get an error. We can't multiply the sequence by non-int of type string. Whereas if we convert x and y to integers first, then this is going to work. So this is one time when you have to worry about data types. The other time is when you want to increase the efficiency of your data storage. And in general, the order from most to least efficient is Boolean, which is just a true or a false object. Integers generally take up less space than floats. then floats, and then strings and objects are more memory or disk space intensive. So how do we measure this? Well, it's how many bits they consume. So if you have a 64-bit integer, that's the default, it can represent integers from minus however many trillions or gazillions this is, to plus 922 and so on. Well, you can reduce the size of your object by half by going from int64 to int32. But then you can only represent numbers in this space. From minus 241 is this some number of billions to the same in positive space. You can also use int16 and int8. Use these, but make sure you're not going to have very large numbers there. And you can also have unsigned integers, which are again more space efficient, but then you can only have positive numbers only. We can also have the same different bits for floats, like float 64, float 32. And here, rather than the range, it's the precision of that floating point number which is affected. So let's use info to get the memory consumption of our data frame. So I'm just creating a pandas data frame which just has a lot of ones. And I'm going to use info. It tells us our columns, but it also tells us that this data frame is using 390.8 kilobytes of memory. So as an exercise, pause the video here and see how your memory utilization changes if you convert this float 64 here to int16 or int8. First of all, predict how this is going to affect your memory usage, and then see if you can check that in practice. So what did I do here? Well, I'm just going to change this column to as type int8. And our 391 kilobyte data frame has now gone to 49K, an 8-fold reduction, which makes sense because we're going from 64-bit to 8-bit, so we use 8 times less memory. What about a less trivial example, using the voting data set that we had before, the precinct level voting? So here we have lots of int64 columns, and our memory usage is 2.4 megabytes. So again, pause the video here and figure out what's the smallest and most efficient data type that you could use for all of these columns. So how are we going to go about this? Well, first of all, let's look at the maximum value of each column to see what data type might be appropriate. Maybe we do have a gazillions of votes in each of these precincts, and so we do need int64. But my guess is we can be a little more economical. So let's use the max operator to get the maximum value with the column. So let's drop the SR precinct column because that's a string. And then for each of these columns, it tells us our maximum number. So for example, in our district, it's 223,000. And for votes for Democrat for Senate, the most is 972,000 and so on. And then, well, what's the max of all of these columns? It's 5.7 odd million. So this isn't going to fit into an int16 object because that maxes out at 32,767. But we could use int32. So I'm going to loop over our columns. And if the data type of this column is not an object, so I'm going to skip our string column, I'm going to convert this column to a 32-bit integer. And now we see that our data frame has now gone down to 1.2 megabytes. And let's check our data is unaffected. Yep, we get the same maximum as we did before. Which isn't the case if we convert it to int16. So notice that before we convert this, our maximum in this column is 972,000. But this is a warning. If we convert this to 16-bit integer and then ask for the maximum, we don't get a warning or anything. There's no error that's raised. Rather, it just garbles our data, and we get 2,175 as a maximum. So this is a health warning. Be super careful when you're changing the data type to a more efficient column, because you might lose some higher values. Another way to deal with this, rather than loading this into memory in the first and then changing the first place and then changing the data type, you might think, well, I'm going to have a problem if I have a large CSV because it's not going to be able to load in the first place. Well, pandas can skip columns that you might not need, it can skip rows that you might not need, and it can also force particular data types. So the CSV reader option has quite a lot of options. So you can use those particular columns here, and you can also specify the data types. So what do we see here? We can just use the columns SR precinct and R2 prop 14, and then we can pass a dictionary to the dtype argument, and we can say, hey, we want SR precinct to be a string, but we want prop 14 no to be a 32-bit integer. So we see, hey, SR precinct, it's now an object or a string. Prop 14 no is what we asked it to be, a 32-bit integer. And we didn't tell it anything for prop 14 yes, so it did the default, which is a 64-bit integer. And we're only using 84 kilobytes of memory. Again, imagine you have a data file which is huge. This can make a difference, being selective about the columns you read in and telling pandas to be a little smarter about the data type that it assigns. So data types are a really important way to manage your memory with large data files. The other method we can use is sampling. And sampling, in a statistical sense, is often useful because there are diminishing returns in terms of predictive power to the size of your data set. So in other words, going from 1,000 to 10,000 is much more useful than going from 10,000 to 20,000. Going from 1 million to 2 million is much more useful than going from 10 million to 11 million. In statistical terms, if you remember basic stats, your standard errors are related to the square root of n, not by n, the size of your sample. So let's recreate the ADU prediction model that we saw in the classification notebook a few weeks ago. So this code is identical to what we had before. We're reading the permits, we're adding our dependent variable, and we're splitting the data into a train and test, and then we're estimating a random forest classifier and a confusion matrix. Well, what happens if we estimate this model on just half the data? Well, let's use the sample function in pandas. This is taking a random sample of just half of our observations. So this can be useful for memory, but also for computational reasons. It will run a lot faster. So what happens if we run just half? Well, it's not so bad. Well, we got 84 true positives here. We got 195 here. But remember, our new data set is only half the size. So we doubled this, we got 168 true positives if we extrapolate to the larger sample. So our machine learning model is not quite as good, but it's not far off, at least measured through this fraction of true positives. Another way to do this would be to estimate the model on a small sample of the data, to look at the feature importances, and then run your model on the full data, but only use those features which turned out to be important in the sample, and ignore the ones that don't increase the predictive importance. They have a low MDI measure. I'm going to leave that for you as an exercise, but sampling is a way to reduce the computational time and also reduce your memory requirements for a data set. For example, you don't even need to load the low importance variables into your data set in the first place. So key takeaways here. Start simple. Most big data sets can be handled on a laptop through being judicious with your data types and through working on a chunk of your data at any one time. And you'll rarely need to do more of this with some typical data sets in urban planning and urban studies. But if you do, if you work at university or study at university with a cluster computer, something like the UCLA Hoffman 2 cluster can be really useful. And cloud service providers are also there if you need them.